So like I say, the key thing is to eliminate the moisture traps to prevent this active corrosion. There's a few pictures here. This was the one that failed due to the paste and the corrosion near the crack. This had a lot of this paste on it. Again, it seems to be relatively unique as to why that aircraft had so much in it. Some areas, some aircraft have been found with small amounts, but again, it doesn't seem to be that common. But this is now all being cleaned, and these are all now sort of shiny and metallic, and that's how they look. So it's before we fly it, it's clean shaft and remove any paste if there is any. And the first stitching, which was caused by moisture trapped in this hole in the plastic plug, which is believed to be potentially even just sweat from the guy that actually fitted it. But because of the shape of the plastic part and the shape of the hole weren't quite the same, that was very neatly sealed in and trapped. And it had exactly the same idea in that the water was pressed against the part. And again, it's in the same part of the weld, so you had the potential for the latent stress was in that particular weld, and these things came together to allow the crack to initiate and then develop. So first of all, you eliminate the moisture traps and get rid of the possibility of water being trapped there through paste that's already in place. Then the oil jets that spray inside, you can just see the spraying through one of the holes here, have been redesigned, and there's new parts are being fitted to allow the oil spray to be much more dynamic and also to cover a much bigger area. So this whole area is now drenched in oil, whereas before it was apparent that the oil coverage wasn't that good. So it has another effect of improving the lubrication of these gear splines, which of course reduces the amount of potential paste or sludge that gets produced as well. So it's kind of a double whammy having this improved oil jet. And it also keeps the whole weld zone clean and prevents any moisture from getting in or being trapped. In addition, once we do start flying, in fact we've done this already, all the shafts have been inspected, a very clever ultrasonic inspection system has been developed by Eurocopter. It's specifically tuned for this region of the aircraft, so it's been specifically developed purely to look for cracks in this part of the gearbox. So the shape of the tool fits into the side of the gearbox. We have to remove one or two pipes on either side. So you put a camber in one side, and then the actual tool itself fits in the other side. It's shaped and designed so that it can only really go in one place. It clamps onto the shaft, and then you rotate the shaft, and you can do a full 360 inspection of that bevel, the weld area of the shaft. So it's the frequency is tuned so that it matches the size of the part, so it's as accurate as it can possibly be. The guys are routinely in the testing phase have been able to pick up cracks as small as 2 millimeters. So it's a very accurate and relatively easy to do inspection. So it ensures early detection of very small cracks pre-flight, and the inspection regime is either every 8 flight hours if you're flying the aircraft at full power, which is what we all intend to do, or it's an 11.5 flight hours if you fly at reduced power. There's not too much benefit to that, to be honest, because you're flying the aircraft more slowly, so you actually end up doing virtually the same number of flights, whether you fly it slowly and inspect every 11.5 hours, or if you fly it at normal speeds and inspect every 8 hours. So they're effectively the same thing. This will be carried out, 8 flight hours is effectively daily, so these will be going on, the aircraft will be inspected pretty much every night, unless they've not done any flying. These analyzers, they record what's been done, so you can, the data that's been collected can be emailed to Eurocopter, or even any remote sites around the world can get cross-check and verification of anything that's been seen. And we've got to keep complete records of all the aircraft and all the checks. Another barrier which has been put in place is the for the flight crew, which is assuming, this thing is so good, and the inspection period is 8 hours because the propagation is 20. So you're going to have to miss 2 inspections for a crack to actually get big enough to fail in flight. So there's at least 2 chances for the inspection crews to find a crack. And given that they can potentially spot them at 2 millimeters, they can definitely catch them at 5 millimeters, and anything bigger than that just stands out as a massive, great spike on here, and it's actually pretty hard to miss. We're not expecting any shaft to crack because we understand the issues, and we're removing the moisture. If one does crack, we're going to catch it on the ground with the inspections. But a further barrier, which we don't really need but is in place on top, is an in-flight system for the crews. Now this relies on the HUM system, the Health and Usage Monitoring System, which is a series of accelerometers around the aircraft, looking at the vibration properties of various different parts. And there's one channel which is it's called Mod 45 because the bevel gear has actually got 45 teeth on it. So that's the channel that we're really looking at. And the vibration spectrum of that changes once the crack has got to about 40% of the way round. So at that point, and to put it in perspective, the shafts actually fail when the crack gets 90% of the way round. So there's still a lot of time when the in-flight HUM system will pick it up before the shaft will actually break. And what we get is there's dedicated warning lights fitted to the flight console in front of each pilot. You can see they're quite prominent, right in your eye line, which will make you look down to this panel, which is the HUMS panel, and on there we get the various different warnings. There's various different things that can happen because the system itself can fail. We can get no data from that particular part of HUMS, which again will be alerted to the pilots, or if there's actually a crack detected, we'll get this Mod 45 exceed. So the vibration, if this was a graph, the vibration will slowly increase. The red line where it triggers is right down here, and the point where it fails is right up here. So the trigger point is it's very low. So if that trigger point gets exceeded, because this part's starting to vibrate now more than it should be, brings on the lights, the crews will see what they've got, and at that point, we've got 2 hours to land. Now, we've actually got nearly 4 flight hours before you would expect the part to fail. But with the usual aviation margins of safety, we're not allowing 4 flight hours, it's 2 flight hours. And in addition, the crew will be reducing power. So you reduce power to reduce the stress through this now cracked part, and you must land within 2 hours. So there's no ditching, there's no emergency as such. You've got 2 hours to fly back to a maintenance base, and there's not many places, to be honest, that aren't within 2 hours of either Aberdeen or Sunbury or Scatster. And one of the things we're looking at is that we won't be flying to those places that are. So we can rely on the fact that the crew will be able to fly back to a maintenance base. And that's it. So it's not if it does happen, if all of these other barriers have failed, for whatever reason, it's incredibly unlikely. And you actually get to this point, even at this point, the aircraft will be recovered back to a maintenance base safely, and then will be inspected to see if it's a real alarm or a false alarm.